at the beginning of this section, I want to work on some conformations with you, and I have my uh, molecular model with me. Conformations, what is the definition for conformations for alkanes is that they are different arrangement of atoms that result from rotation around the bond. So, for example, if you have ethane molecule, first of all, methane cannot have conformation because it only has one carbon. Now, for ethane, for the smallest alkane, if you have this conformation, if you have this molecule, you have 2 carbons and 6 hydrogens. Let's say hydrogens are aligned with each other, so it will show this conformation, right? Let me hold it here. If you 60 degrees rotate along this bond, what happens? 60 degrees, if I rotate along the bond, then I will have this, or this. You see? So, maybe I should have drawn, yeah, okay. Hydrogen up, hydrogen towards you, away from you, and down, towards you, away from you. So conformations are formed by rotating 60 degrees along the bond. Now, what we want to do is to draw these conformations in a new style, which is called Neumann projection. It's very important, you need to learn it at this point. Neumann projection. So I'm going to draw each of these using my molecular models to draw the Neumann projection. For Neumann projection, instead of sidewise, you need to look at through one of the carbons. Okay? Here the molecule is simple, just 2 carbons, so you just simply look at one of the carbons. Okay? Now, we have 2 carbons, right? We always focus on 2 carbons. The first carbon, which is closer to your eyes, we show it as a dot. Okay, so this is the front carbon. The back carbon, which is farther from you, we show it with a circle. So this is the front carbon, and this is the back carbon. All right? Now we also have some hydrogens, we need to show them, right? What is the first thing you see? The hydrogens which are closer to you, right? One in 12 o'clock position, one in 4, one in 8. And they're connected to the front carbon. So which one was front carbon? Dot. One in 12 o'clock position, one in 4, one in 8. Okay? So these are my 3 hydrogens that I see in the front. But you also have some hydrogens in the back. If I move it a little bit, you will see them. But you don't actually see them that much because these front hydrogens are covering the back ones. So it seems like they exist, but very close to the front hydrogens as far as the angle, right? Almost 0. So those are the hydrogens. So it seems like the carbon in the front and the hydrogens in the front are covering or eclipsing the other atoms, right? So we name this Neumann projection as our eclipsed conformer. Eclipse conformation, because just like the moon eclipse and sun eclipse, we have covering here, right? We don't actually see the second carbon and hydrogens, just a little bit, and we need to show them like this with the minimum. Here we show like 0 degrees between the 2 hydrogens because they are covered. Now, the second one, We said for the second one, we rotate 60 degrees. That's the 60 degrees. Now look, you see? You see everything now. Again, the front carbon as a dot, the back carbon as a circle. Now, let's take care of the front carbon first. What do you see connected to front carbon? One hydrogen in 2 o'clock, one in 6, one in 10, right? So let's show them. Front carbon means the dot. 2, 6, 10. And now you see the hydrogens connected to the back carbon. 12 o'clock, 4 o'clock, 8 o'clock. The back carbon means the circle. 12, 4, 8. Hydrogen, hydrogen, hydrogen. Now the distance between hydrogens is 60 degrees. Okay? Between every two hydrogen. That's for ethane. And most of the times, ethane, 99% of the molecule exists in this conformation. Why? Because when you have eclipsed, we're talking about tiny molecule, so we have strain between the hydrogens. Although they are tiny, but we have some torsional strain, means we have some strain between the two atoms that eclipse each other. And you will see in the other molecules, when these groups are not hydrogen and they're bigger, the torsional strain is becoming bigger and bigger, and the molecule becomes less stable. But when you rotate 60 degrees, what happens? Do you see any torsional strain here? No. Do you see any torsional strain here? No. Any here? Any here? No. So the one which is not eclipsed and there are 60 degrees between the two hydrogens, between each two hydrogens, we call them staggered, like the word staggered that you have everywhere. Okay, so we have so far eclipsed and staggered. Learn them. We just drew them for ethane. What if we have, instead of what did I prepare? Okay, I prepare something on my own, not based on the study guide. I'm working on 1 and 2 dichloroethane. 1 and 2 dichloroethane. Okay, if we draw it, it's going to be CH2Cl, right? And CH2Cl. All right. So in my molecular model, I'm showing the chlorine atoms with green color. All right. So let's take care of which one do you want? Let's take care of the eclipse first. All right. Everything aligned. 2 carbons. What do you see connected to the front one? A chlorine, 12 o'clock, and 2 hydrogens in 4 and 8. Chlorine, 2 hydrogens in 4 and 8. And the same thing for the other carbon. It's extremely unstable because the chlorines are big and they have some torsional strain. Now let's rotate. It doesn't matter which one. You can hold one of them or imagine you're holding one of them and rotate the other carbon. You cannot rotate both of them at the same time. So look what happens. This one was eclipsed, right? Now, what do you have? connected to the front one. 2 o'clock, chlorine. 6 o'clock and 10 o'clock, hydrogens. 6 and 10 o'clock, hydrogens. And in the back you have 12 o'clock, chlorine. Hydrogen 4, hydrogen 8. Okay? If you keep rotating one more time, what do you see? This is staggered. And I'm going to introduce a new one to you, a new conformation. When you rotate one more time, you have 2 and 10 o'clock hydrogens to the front carbon, and 6 o'clock chlorine. To the back carbon, what do you have? What do you see? 12 o'clock chlorine, 4 and 8 hydrogens. 4 and 8 hydrogens. You see, chlorine atoms have 180 degrees distance from each other. Why do we emphasize on chlorine? Because chlorine atoms are the largest, right? And they have the least torsional strength. So we call it anti-conformation. So by changing the groups, we have the different rotation. We have different conformations. If you have other groups than hydrogens, then you can have anti-conformation as well. Okay. Now, 1 second to prepare my. Okay. Page 9. Page 9 is asking about butane first. By increasing the number of carbons, you need to pay more attention to the location of carbons. CH3, CH2, CH2, CH3. Now, pretend that we don't have the molecular models. Page 9 is asking, draw a Neumann projection of butane sighting down C2C3. So you are always told which carbons. Sighting down C2 and C3. So you put your eye here, this is your eye, eyelashes. Okay, so your eye is here. So the front carbon is carbon number 2. This is the front one. And the back carbon is carbon number 3. Alright? So let's see what is attached. It just says one Neumann projection. That doesn't specify which one. So let's just go with the one with the 60 degrees distance from each other. So to the front carbon, what do you see? You see 2 hydrogens and a CH3, correct? So since we don't have any specific conformation, let's just put CH3 on top and 2 hydrogens on 4 and 8. Okay, 2 hydrogens and 1 CH3, and the rest is connected to the front, to the back carbon. Now to the back carbon, what do we have? 2 hydrogens and 1 CH3. So 2 hydrogens and 1 CH3. That's what you see. So again, because it was not specified what type of conformation, I just drew it on my own, like whatever I want. So CH3, CH3. They are not methyl groups. That's a part of the chain. Okay? That's how you see it from putting your eye on the second carbon. The next one is 2 and 3 dichlorobutane. 2 and 3 dichlorobutane. So we have 2 chlorine atoms. Again, citing down C2C3 doesn't mention what type of conformation, so just work. All right, so one more time. This is the front carbon, this is the back. What do you see connected to the front carbon? 1 hydrogen, 1 CH3, 1 Cl. So put them wherever you want. One, but they have to have 120 degrees away from each other. Cl, let's put CH3 here, and then hydrogen. Doesn't matter which one goes where at this point. Here for the back carbon, hydrogen, CH3, Cl. I would put hydrogen here. I would put CH3 here, and I will put Cl here. You could have put eclipsed, but I didn't work on the eclipse. I mean, I thought it's easier to see it. So, which one of these, by the way, you think is more stable? Which one of these molecules you think? You have a strain between these two, you have a strain between these two. So keep it in mind because we're going to work on some energies. You can work on the rest. Let's we can work on the energy of this one, since we have on page 10, we have a little table. We did not have the strain for chlorine, that's why I erased that. So let's determine the strain. The strain between hydrogen and hydrogen. You see in table 4.3, the strains are given, the interactions are given in eclipsing only. So let's change this to eclipse. Why eclipse? Because we said steric strain in eclipse conformation is higher. So again, let's have CH3 here, hydrogen, hydrogen, a hydrogen here. I've rotated the back carbon, the CH3 here, okay, and the hydrogen here. So according to this table on page 10 of your study guide, hydrogen, the energy for hydrogen eclipsing, the strain. Hydrogen is 4 kilojoules per mole, or you can use kilocalories. I go with kilojoules, depends on what is asked. But here it doesn't matter. The energy of hydrogen CH3 eclipsing is 6. So hydrogen CH3 is 6. So I have 2 of them, right? So the total steric strain energy is 4 plus 6 plus 6. So what is total? 16 kilojoules per mole. That's how you calculate the strain energy. What else do we have here? One more thing. I didn't name this compound. I named this eclipsed. I named this staggered for hydrogens. But what if you have CH3 and hydrogen 60 degrees away from each other? You call it gouge. So now you would say, come on, so many names, we are confused. Eclipsed, 0 degrees between groups, whatever it is, hydrogen, CH3, whatever. Staggered, 60 degrees between hydrogens. gouge 60 degrees between hydrogen and any groups like CH3 or Cl, okay? And anti, when you have 180 degrees between groups like CH3 and Cl. So by increasing the number of atoms, you have more names to be worried about. Okay, not bad. Let's work on page 14, because you just need to play with different compounds. And by the way, I'm not going to give you very large, very long compounds, because I don't want to confuse you. I just want you to know what you've learned about these compounds. So for page 14, rank the following conformations in order of increasing energy. Okay, let's draw them. We have compound B, compound B, and compound C has compound C, and finally compound D is now. The stability depends on the steric strain or torsional strain that we have between the groups. Now let's look at the groups. You have a torsional strain between these two ethyl and methyl group, and again between these and these. So you have two 60 degrees away from each other and two eclipse. So you're going from, in order of increasing energy means less stability, means going towards eclipse. So let's find out which one has the highest torsional strain. You look for the eclipsed one, right? Eclipsed and eclipsed. There are 0 degrees between the groups. So ethyl and hydrogen, methyl and hydrogen, methyl and ethyl. And it's not maybe the correct term that I say ethyl and methyl, but because I just see them as this, but This is between CH2, CH3, and CH3. And here you have the same between methyl and ethyl, and two hydrogens. So if you calculate the energies, the stereostrain energies from a table in a book, you will see that these are the same, right? Now you have another one, but here you have CH3 and hydrogen, which is a small, CH2, CH3 and hydrogen, which is a small. So this is the most energy. Then is B, and now then decide. So eclipsed groups always have the highest energy and less stability. So let's decide between A and D. Between A and D, you see here it's a little bit crowded. These guys can have a torsional strain with each other, but here they are more separated from each other. So you would say D is the lowest energy, most stability, and then A, and then B and C. I will work on one more on page 14, and I will leave the other one for you to calculate the torsional strain, or to calculate the energy. Let's calculate B together. You can use the table on that you had previously, or any other tables you have in your textbook, or you find it online. So according to that table, the torsional strain between hydrogen and CH3 eclipsed is 6 kilojoules per mole. And you have 3 of them, right? So what is the total torsional strain here? 3 times 6 kilojoules per mole, which is 18 kilojoules per mole. Okay, this is as far as the conformations. You need to know how to draw the Neumann projections, how to name them, eclipse, staggered, gauge, and anti, and how to calculate their torsional strain. Don't forget, eclipse is the most unstable, or the least stable, because of the highest torsional strain, but the staggered and anti are always less energy. Don't forget to have enough practice until we finish this chapter with cyclic